Hi, everybody. It is time for our next video lecture. I think this is our 31st video lecture, Melissa's telling me. Okay, that's good. Today, I want to do the following. First of all, I have homework papers to pass back to those of you who are here. Melissa, I have yours. This is homework number 4. Megan, I have yours. Audra is here. I have hers. Jonathan is here, and I have his. And maybe a few more people will come in. The next thing that I wanted to do, I can't remember what I had promised last time in terms of the conclusion of the class, what I would provide for you. But I do have a study guide for Test 2. So Test 2 is just a little over 2 weeks away. And so here is a study guide for it. I don't know how clearly it printed out. I will also put this up on Blackboard. And today, we're going to start the last main concept of the class. So we got just a little over 2 weeks to go. And of regular class period. And today is the last, today we'll start the last major concept. Okay. So what I pass back to almost everybody is their homework, graded homework, as well as the study guide. You submitted it. It's in my office. Okay. Sorry about it. I'm very apologetic. I'm cleaning my office now to find the homework stuff. Okay. So I'm very sorry. Thank you for being patient with me. The concept we're starting today is that of continuity, and it's closely related to limits of functions in certain situations. It's exactly the same in a certain situation. So we're going to learn about that today. So this is chapter 4 of our text. It has to do with continuity. Okay, one of the beautiful things about mathematics is we say exactly what something is. So here's what it means to be, for a function to be continuous at a point. So here's the definition. And first of all, we let A be a subset of R, the setup for continuity. F go from A into R, and here's the first difference between continuity and limits. Here's the first difference. We let C, normally we say be a cluster point, but here we don't. We say let C be an element of that. So we don't know whether C is a cluster point or not. Okay, but it's in that. Okay. Then F, we say that F is continuous at C if for each epsilon greater than 0, there exists a delta bigger than 0. Now the delta can depend on epsilon and it can depend on 0. Okay? Such that for all x element of A with, here's another difference between this definition of continuity and limit definition, with x minus c being less than delta. The difference here is for limits we had 0 less than x minus c. But here we don't have it. Then absolute value of f of x, here's another difference, minus f of c. Normally we put L for limits of functions, but here's f of c, will be less than epsilon. Here's the idea. So the idea of continuity is the following, is that we can make the output values that's f of x be arbitrarily close to f of c, that's an output value, for all input values, that's the x's in the domain of A, that are close to C, right, close enough to C, including C. Pictorially, if we think of this as C, and C is in the domain of our function f, maybe our function looks like this. I don't want to. Okay. This is my function f. Here is f of c, the output value. Okay. What we're saying is that you can force all of the output values, those are y values, to be within epsilon units of f of c. So if this is my epsilon, epsilon above, epsilon below, that's going to hold true for all x values within some little region about c. That region about c is delta units about c. So here, no matter what distance you want me to have the y values within f of c, I can make that happen if f is continuous at c by choosing the appropriate delta about c. So we can make the output value, this idea, we can make the output values f of x be arbitrarily close to f of c for all input values, that's all the x values, close enough to c, including c, if f is continuous at c. Okay, so that's the idea.
Question.
Yes, sir.
Is it equivalent to say that the function is continuous at c if the limit as x goes to c is equal to f of c?
It is when C is a cluster point. Okay. When it's not a cluster point, we get something a little different. Okay. Because we can't take the limit if C isn't a cluster point. Okay. But yes, and that's something that we may prove today if we get to it. Okay. Well, let's look at an example. The example here that I'm going to give is going to be reminiscent of examples for limits. Okay. They're going to look very similar. For a limit problem. Example. Show, let's say, f of x equal to, let's say, minus 3x plus 5 is continuous at, let's say, x equal to 2. So my c in this problem is 2. My f of x is minus 3x plus 5. Well, how do I do this? Well, I've erased the definition, but that's what we use. So what did the definition say? It says, hey, no matter what epsilon you give me, so I'm going to let epsilon be greater than 0 be given. Just like we need a delta, which is greater than 0, such that what? For all x in the domain, so here the domain of this particular function is R. So for all x in R, with the distance between x minus the c, well, I'm just going to write down c in this case, okay? We'll fill in the particulars from this problem in the next line. Is less than delta, then, well, it says f of x minus f of c will be less than epsilon. That is, we need a delta, so for the particulars of this problem, such that for all x element of R with x minus, what's c? 2. Being less than delta, then f of x, what's f of x? Oh, let me put in what f of x is. What is f of x? We write it in terms of x. What is it?
Minus 3x plus 5.
Yeah, minus 3x plus 5, minus, it says f of c. Well, that's going to be f of 2. So I need to know what f of 2 is. So what's f of 2? By sticking 2 for x, it's minus 3 times 2. That's minus 6 plus 5. I think that's minus 1. Okay, it's less than epsilon. So this is what we want to have happen. We want the output values to be within epsilon distance of minus 1, because that's what f of 2 is. It's minus 1. So we want, let's concentrate on what we want, and maybe we can get it through what we can control. So we want absolute value, what would be, it looks like it would be minus 3x plus 6. We want that to be less than epsilon. Now what I get to control is the absolute value of x minus c. So maybe I can write down what I want in terms of what I can control. We want, well, I can factor out a minus 3, and then I have x minus 2 to be less than epsilon. So we want, so Megan, I want to clearly state what it is that I want as opposed to what I know, okay? So I haven't really proven anything. What I'm trying to do is narrow down what it takes to be sufficient for us to prove what we're looking to do. So if I can get the absolute value of minus 3 times the quantity x minus 2 to be less than epsilon, I'd be in good shape. Okay? So here, Melissa, we want, how can I rewrite the absolute value of a product? The absolute value of two things multiplied together, Melissa, is the absolute value of the first times the absolute value of the second. So what's the absolute value of the first here, Melissa? What's the first? Where am I looking? Right here. What's the first? It's minus 3. What's the absolute value? So we want 3 times the absolute value of x minus 2 to be less than epsilon. Now, Melissa, everybody else in the room, what I get to control, I get to pick the delta, so I get to control what x minus 2 inside the absolute value of that. I get to control how small that is, okay? Well, if I solve for the absolute value of x minus 2, that means we want the absolute value of x minus 2 to be less than epsilon over 3. Well, the delta I need to pick is sitting right in front of me now. So, Audra, really, it's a comparison. Here's what I want, but I get to pick the delta to make the absolute value of x minus 2 and, be less than whatever I want. Well, what do I want the absolute value of x minus 2 to be less than? Not just 3, but epsilon over 3. So it should let delta be epsilon over 3. So that's sufficient for me, Megan, to give the proof, Brad. Okay? But you can work backwards, okay? Or, you know, I should say this is the working backwards. You can work forwards, but I won't need that. That isn't a necessity for me. So we've seen in other of these types of proofs, okay? So here's what I mean. but I can work forward. So for all x element of R with x minus 2 being less than epsilon over 3, we have, I'm just going to write down the following implications. We have 3 times absolute value of x minus 2 is less than epsilon. That is, which implies minus 3 inside absolute values times x minus 2 is less than epsilon, implying, if you stick in the minus 3, the absolute value of minus 3x plus 6 is less than epsilon, implying, so I'm just rewriting everything in terms of f of x minus f of c. This would be minus 3x inside absolute values plus 5, that's my f of x, minus 1, okay, is less than epsilon. Thus, the absolute value of f of x minus f of 2 is less than epsilon. So that's how I know that f of x is continuous at 2. Let me write up that conclusionary statement. Listen, I'm going to write up the conclusionary statement that f of x is continuous at 2. But before I do that, what I was saying is once you find the delta, that's sufficient for me. You don't have to go through this. Why am I going through this? Just one time I wanted to show you that if you let the absolute value of x minus c, that's x minus 2 in this case, be less than the delta that you chose. You have to choose the delta, okay? But the delta we're picking is epsilon over 3. Then as you progress from there, what does that imply? It will imply, in this case, that f of x minus f of 2 inside absolute values be less than epsilon. And that's what we needed to have happen for f of x to be continuous at 2. That's right. So let me write the conclusionary statement. Continuity of linear functions are easier to prove because we can get what we want to have happen in terms of what we can control, the x minus c. We can do that every time. Other functions are tougher. They're tougher. But I'm going to take the simplest of linear functions and prove that. So here's a fact that it's continuous. If f of x equals to b. What do I mean by b? B is just a number. So I'm thinking f of x is a, what kind of function is that? Constant function. And c is a real number, as a constant function defined on all of R. Then f of x is continuous at c. And so here's the proof. Our proof is going to work just like the other one. So we're going to let epsilon be greater than 0 be given. What do I need? We need delta. Yeah, that's right. A delta greater than 0, such that for all x element of R in this case, that's what A is, the domain of the constant function, with, here it is, x minus c being less than delta, then absolute value of f of x minus f of c will be less than epsilon. So let's concentrate on what we want to have happen and see if we can relate that to what we can control, which is the absolute value of x minus c. Well, we want f of x minus f of c to be less than epsilon. But let's put in the particulars for this problem. Brad, what is f of x? Every time, f of x is equal to b. So what do we want? We want the absolute value of b minus, Brad, what's f of c? What's f of anything, Brad? Okay, so f, that's fine. So this is a not so bad question to answer. You can get it, and everybody else can too. F of x is a constant. It's always b. If I say, what's f of 17? Your answer is b. If I say, what's f of 23? Your answer is b. If I say, what's f of minus 1,000? Your answer is b. What's f of c, Melissa? What's the answer, anybody? B. Every time it's B. So we want this to be less than epsilon. I'm just making a substitution, okay? For each one of these parts, I'm just substituting. Hey, Megan, what's B minus B? What's absolute value of 0? Yeah, well, we want this to happen. We want 0 to be less than epsilon. Well, wait a minute. We're choosing epsilon. Epsilon was given to us. That is greater than 0. So we have that. Well, epsilon is greater than 0. So it doesn't matter. It didn't have any dependence here on delta. It doesn't matter what delta we pick. Any delta will work. Any delta greater than 0 will work. Just to give a specific one, say delta equal to 1. And that's my proof. So as long as I give you the delta, and I'm giving you a reason why that delta will work, I don't have to work backwards. So that's the proof that a constant function is continuous at any point in its domain. Pictorially, I don't know, let's say b is a positive number. So this is my x-axis, if you will, if I'm looking at f of x. And let's say this is b. And let's say this is c. So there's my function. There's f of x. It's b. It's always b. Look, it's a straight horizontal line. That's the best I could do. Look, they give me some epsilon here. I'm looking kind of in this area right here. I want to make sure that the output values are in this band. I want to make sure that happens. And what I'm saying is, what I get to do to make sure that the output values are in this band is by narrowing how close I am to C. Getting real close to C. But, you know, when I look at the output values, they're always in this band. It doesn't matter how close to C you are. If you're that close to C, in that region C, the output values are always going to be within that band of B, because they're going to be exactly B every time the output values are. Is that okay? So I just happen to pick delta equal to 1, but I could have put delta equal to 1,000. It doesn't matter. Is that okay? As long as you're in that region about C, the output values are going to be really close to B. Matter of fact, in this case, they're not only going to be really close, they are going to be B. Is that okay with everybody? Okay. Anybody with any questions about what I've said? Well, John mentioned something that I want to talk about next, and it was about comparison limits to functions and continuity. Except I want to do it kind of backwards from what he said. That I'm not going to say the comparison immediately. I'm just going to say, what if C is not a cluster point? Look at that So here's the fact. If A is a subset of R, F goes from A to R, and C is an element of A where C is not a cluster point. That. Then the conclusion is F is continuous at C. Man, if you're not a cluster point within the domain of the function, then the function is automatically continuous. Well, it's got this word cluster point. We talked about cluster points. We've seen examples of it. It's always good to get a review. So let's take a second. Let's go over here. Let's remind ourselves, what does it mean to be a cluster point? So it's a definition. If we let A be a subset of R, then C element of R is a cluster point of A if for each delta greater than 0, there exists right, X element of A with X being different than C. So there's some guy in A that's not C, such that the distance between X and C is less than delta. What does that mean? Well, what that means is to be a cluster point of A, that point C is something that A, if you will, is right next to, or there are points of A right next to it that aren't C itself. So if this is A, from -1 to 3, that's A, then 3 is a cluster point. Because no matter how close you want me to get to 3, there's something in that little region that I just put around 3 from A that isn't 3. So 3 is a cluster point. The point is having points from A getting arbitrarily close to it, okay? That are not C. That's what it means. Okay, well, let's turn back to the fact that I said. We're saying the following. We're saying, hey, if you're in the domain, but you're not a cluster point, then you're automatically continuous. The function is automatically continuous. Oh, wait a minute. What does it mean to not be a cluster point? That means there aren't things arbitrarily close to C from A. What that means is really C is out there by itself. It doesn't have anything close to it from A, besides maybe C itself. So C's in A, but it's off there by itself. Man, it's standing alone. That's what's happening. Okay? Okay. So here's the proof. Let F go from A to R, and C be an element of A with C not being a cluster point. What do we want to show? We want to show that F is, what's our goal? Show it's continuous at C. I'll write that down.
Does A have to be a subset of R?
Yes. I didn't write that down. I'm just kind of assuming. That's right. That's, to be careful, I should have said it. We want to show that F is continuous at C. Well, I only got one way of doing that. What is the way of doing that? That's the definition. So what's the definition to start off with? It says, well, let epsilon greater than 0 be given. We need to find this delta. We need a delta greater than 0, such that for all X element of A with X minus C being less than delta, then f of x minus f of c is less than epsilon. What do I know? I know that C is not a cluster point. What's it mean to not be a cluster point? It means C's in A. We know that part. It doesn't have to be in A to not be a cluster point. But in this case, we know it's in A. But what it means is in A, and there's nothing besides itself from A that's close to it. What do you mean close to it? That means there's got to be some region about C that there's nothing from A in that region except for C itself. That region that I'm going to form about C is going to be my delta neighborhood. Is that okay? So I'll say since C is not a cluster, of A, then there exists a delta greater than 0 such that the only x element of A with x minus c being less than delta is what? X equal to what? C. C. C is the only point from A that's close to C. Okay? Within this particular delta units. Okay? So, for all x element of A, with this particular delta being used, such that x minus c is less than delta, then what about the absolute value of f of x minus f of 6? Wait just a second, let me get out of the way. I haven't said anything. Look, I'm talking about the x's in A that satisfy this. And I want to say, what can I say about, for all those x's, their output values, what their distance is from F of C. So I'm talking about this set. All the x's in A such that their distance from C is less than delta. Wait a minute, what did I just say about all that set? What's in that set? What are all the points of A whose distance from C is less than delta? Just C. C's the only guy in A that's within delta units. So C is the only point we're talking about. The only x we're talking about is C. That's the only one. So what's f of x minus f of c? Well, what's f of x for these x's? There's only one x we're talking about. We're talking about f of c. Okay? Oh, yeah. Here. So this f of x minus f of c is really just f of c minus f of c. Wait a minute, what's f of c minus f of c? 0. Well, that's equal to 0, which is definitely less than epsilon. So f of x is continuous at c.
We don't have to say delta equals 1 in this case because we already said that delta exists, right?
Right, and then we're saying that delta is a fixed number. We don't know what it is.
We don't care.
We don't care, but there is some delta.
Right.
So here, let me write it down this way. So let's say, John, f of x from 0 to 1 is equal to x. That's that. Everybody see what I just drew? F of x equal to x. Remember, that's that diagonal. That's from 0 to 1. That's the only place I'm looking at, that A. Plus, let's look at it at 1.1. Let's look at it, 1.1. This is also going to be in the domain. Let's say that's 2. So f of 1.1 is 2. You guys hear me? So that's why I'm defining f pictorially. And here's what I'm thinking. 1.1 is in A. Our A is the interval from 0 to 1, union with this one other point, 1.1. Well, can you tell me about 1.1 in terms of this set? It's all of this plus this part.
It's not a cluster point.
is not a cluster point. Is that okay with everybody? What does it mean to be not a cluster point? It means I can get some little region about it, delta region about it, such that within that delta region, the only thing that's there is 1.1 itself from A. Is that okay? To be a cluster point, then I get something about it. To not be a cluster point, I get something about that point, and there's nothing in, nothing from A within that little region about the cluster point, the non-cluster point, except possibly the non-cluster point itself from A. So that's what we have. And if you say, look, take all the guys that are in the domain that are in this region. Well, what's that?
Just that.
Just 1.1. That's the only thing in this little region that's in the domain of F is 1.1. So for all the things that are in the domain, of this function that are in this region of 1.1, which is only 1, if you look at its output value, it's really close to the output value of F of 1.1. Matter of fact, they are the same because there's only 1 point there. Does that make sense? So that's how we get it. So it's got to be continuous here because for every x really close to, every x in the domain really close to 1.1, there's only one x in the domain. It's 1.1, really close to 1.1. Then the output values for all those points are really close to the output values of 1.1. Well, they're the same because there's only 1 point in there. Okay? That's what means that. All right. Well, we've said that. So, John, that's kind of the easier case than everybody else about something about a cluster point involving. But what if, or not cluster point? What if we do have a cluster point? And then John said the right thing.
Straw.
So it's a fact. If we let A be a subset of R, F go from A to R, C be an element of A, with C being a cluster point. Okay. Then F is continuous at C. If and only if the limit as x goes to C, since C is a cluster point, I take of f of x equals f of C. It's an if and only if statement. Okay, let's do a proof. So here we're going to let A be a subset of R, F go from A to R, C be an element of A with C being a cluster point. Okay. So this statement that we're trying to prove is an if and only if statement, and that's the setup for both parts, okay? That's the assumptions for both parts. And now the if and only if part, we have two directions. Whoops, I'm sorry. So the first direction is we're going to assume, suppose, okay, we're going to suppose F is continuous at C. What is it that we're trying to show? We must show I'm gonna show what? The limit of x goes to c of fx equals f of c. That's right. So this is like my L in the limit definition, Ultra. How do I show that? Well, I use the definition of the limit of a function, and that is you give me n, you let epsilon, Brad said correctly, be given. And now let's be careful. So here's where we get to see some of the differences, Megan and Melissa, between the definitions of limits of functions and continuity, John, let's see, of a function. What do we need? Now remember, I'm trying to show a limit exists. We need a, yeah, we do need a delta, John, greater than 0. Such that for all x element of A with, remember I'm talking about limits now, with what? That's right. Then the absolute value of f of x minus f of c, that's my L, will be less than epsilon. That's what I want to show. We need a delta that makes that happen. But what am I assuming? What do we assume? We're assuming that the function is continuous at c. Isn't that right? We're assuming that. Now, since f is continuous at c, what does its definition give us? Well, that means there exists, what does there exist?
Delta greater than 0.
Right, there exists a delta greater than 0, such that for all x element of A with x minus c less than delta, then what do we have? We get that f of x minus f of c is less than epsilon. So look, I want the absolute value of f of x minus f of c to be less than epsilon, as long as I'm close enough to. I want f of x minus f of c to be less than epsilon, and I want it to happen for all x's in A, such that the absolute value of x minus c is less than delta and bigger than 0. Okay? What I'm getting it for, I'm getting what I want, but I'm getting it for all x's in A, such that x minus c is less than delta. I don't have the requirement that you have to be, the absolute value of x minus c has to be bigger than 0. It says I need it for these. But when you get it for these, which we do have, you're getting it for all of these. What do I mean? This right here says, as long as x's are in A and they're within delta units of c, the output values are within epsilon units of f of c. What we need to have, that's what we got. What we need to have happen is for all the x's in A, such that the distance between x and c is less than delta, and x is not equal to c. So it says I only need it for when x is not equal to c but close to c. But I've got it for x even equal to c. Is that okay? So here's what I get to say. Thus, I've got this part right here. Thus, for all x element of A with 0 less than x minus c is less than delta, then f of x minus f of c is less than epsilon. What I had covered what I wanted. It was more than what I needed, okay? Because it included C, what I could do. I didn't need C. So that's part of the proof. That's one direction. Then we've got to go backwards. Okay, so how do I go backwards? Well, what are we doing here? We're assuming what? Assume the limit as x goes to C of f of x equals to f of C. What do we need to show? We need to show f of f is continuous at C. Just a few more minutes, we'll end with this statement. I think we'll end with this statement. Okay, so how do I show this? Well, how do I show continuity at something in its domain? C is in the domain, C is in it. So how do I show this? Well, this is using the definition. What do I say?
Epsilon greater than 0 together.
Yep. That's the way they start. What do we need? We need a delta greater than 0, such that for all x in A, with, well, now I'm talking about continuity, so what's the next thing I write?
Absolute value x minus c less than delta.
Then, that forces the f of x minus f of c to be less than epsilon. That's what I want to have happen. Well, what do I have?
Got the limit.
That's right. You know, look, what this is saying is we want to make sure that for all x's that are really close to C, and that includes C, that f of x minus f of c inside absolute values is less than epsilon. What I have is the following. Since the limit as x goes to C of f of x equals to f of c, then we've been given an epsilon, so there exists a delta greater than 0, such that for all x element of A, with what? I'm talking about limit. What's the next thing I'll write?
0 less than absolute value of x minus c less than delta.
Then the absolute value of f of x minus f of c is going to be less than epsilon. So look, what I want to have happen is I want all the x's in A such that x minus c and absolute value is less than delta. Then I get this. What I have is for all x's in A with x minus c less than delta and being bigger than 0. So when I think about what I want it for all numbers, all x values that are within delta units of C, and it includes C. What I've got it for are all numbers really close to, in the domain really close to C, except I don't have it for C. So I need to make sure that it's true, what's it? That this is true, this statement, the output values are really close to f of C, within epsilon units of C. I need to make sure that's true when x is equal to C. Wait a minute, that's stupid. When x equals to C, I mean, it's just easy. Then f of x minus f of c. I shouldn't say stupid, but it's just obvious. This part right here, well, what's f of x? What's x in this case?
C.
C is equal to f of c minus f of c, which equals to 0, which is definitely less than epsilon. So what I had was everything I needed except for when x is equal to c. But when x is equal to c, it's obvious that the output value is really close to f of c.
So in all possible cases, right?
So for all x's element of A with x minus c being less than delta, then the absolute value of f of x minus f of c is less than epsilon. And that is the proof. So we have both things. Yeah, you could say about cases, John, we got it for x's that are different from c, we got it for x that is equal to c. You could say it that way, but I chose just to ignore that type of thinking. All right, give me 1 second here. Let's see if there's something I want to say. Oh, it's maybe a little bit hidden about the aspect of the aspect of C being a cluster point plays in this fact. So, you know, did we ever use the delta so that we have a point from A within delta units of C because C is a cluster point? You might say, I didn't say we used that. The reason that we're having that C is a cluster point is so that we can just talk about the limit. Because we've only defined limits of functions at
Cluster point.
cluster points. So if C is not a cluster point, we can't talk about the limit. Is that okay? So that's the role of C being a cluster point.
What about C being an element of A? Where is that used?
Here it's used because we want to get, John, you asked
We can plug it in.
well, here you said, well, remember what we want is for every x in A with here.
Okay.
And so we know that C is in A, so we got to worry about
We should account for that.
for that. Yes, so that's where it's being used. You have to find that. Okay, well, I've spent enough of your time here.